Warning, the video you're about to watch contains mathematics at the level of differential calculus, also known as Calc 1. All material has an assumed prerequisite of pre-calculus and a full semester course in trigonometry. A thorough review of prerequisite topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This is a second part to graphing using calculus. Now, just to give you a heads up, if you're not watching my videos in the order that I present them and you just stumbled upon this by searching YouTube, this is graphing using methods of calculus without using L'Hopital's rule. And so we have not finished covering all of the graphing techniques required, but this is kind of the part of the introduction to graphing using calculus. If you're looking for the full-blown graphing using calculus videos, it'll probably be around, like, let's say part, I don't know, 6 or something like that. Anyhow, where we left off last time, though, we had just graphed a function and we used calculus, and we used this how-to. And recall, there are a couple pieces missing here. I still haven't filled in that step 3, nor have I fleshed out anything about this step 5 here. So those are still awaiting some further information. But this is the how-to that we introduced last time. And we're going to go through that to graph yet another function. So each step of the way, when I graph this other function, I will refer back to this how-to. I won't quite jump back here, but I'll state what we're doing at that time. So here we're asked to graph the curve f of x is equal to -6 times the quantity x minus 2 raised to the 2/3 power. Going through mathematics the way we learned mathematics, let's go ahead and look for intercepts. And the easiest intercept of all is the y-intercept. So I'll start with the y-intercept. Y-intercept. And that happens or occurs when x is 0. Looking at our function and allowing x to be 0, we get -6 times a -2 to the 2/3 power. And that is actually a little bit of a mess. So I'm going to write that as a -6 times a -2 to the 2/3 power. However, there's a little bit of cleanup you can do here. Not very much, honestly, but you should recall that when you have a rational exponent, the numerator is actually the power, the denominator is the root or the index for the radical. So this is the cubed root of a -2, and then you would square it. The important part there is the squaring part, because when you square a negative, the negative will disappear. So really, that's my cleanup. That's all I had to do there. Note also that this number is left in exact form. It's a good idea to leave your numbers in exact form while you work on the problem. And then at the end, when you're about to graph, go ahead and use a calculator to approximate those numbers to get like a decimal approximation. And as I go through this, I'm going to do what I did last time, which is build a table of values. And I'll just build that table of values off to the right here. So let me go ahead and start that table. And I've actually decided to go ahead and do those decimal approximations while I work through this. I might as well, because we're going to have to plot points eventually, and it'd be nice to know what these values roughly are. So this is roughly a -9 I'm going to go to, maybe I'll just go to 3 decimal places. I'm doing that not because I want to do that for graphing, because honestly, just a single decimal place is good enough for graphing. But 3 decimal places because if you're using an online homework system and it's asking for decimal approximations, generally speaking, 3 decimal places is pretty good. All right, so again, going through the way we learned algebra, we look for the y-intercept, that's the easiest, and then we go for the x-intercept or the x-intercepts. There might be more than one, right? So doing that algebra, you're just gonna let f of x be 0 and solve. So we solve 0 is equal to x minus 2 to the 2/3 power, and we know, obviously dividing both sides by -6, and then raising both sides to the 3/2 power, that x would have to be 2. So our x-intercept is 2, 0. And again, I'll fill that in over on the right-hand side here, 2, 0. Now we graduate from our elementary algebra work, because that's really what all that involved, was some elementary algebra skills. And we move into our intermediate algebra work. So this is still kind of the high school algebra work that we're doing right now. But this part would be, let's go ahead and discuss the domain. So the domain of this function is all real numbers, mainly because you're having the cubed root here that you're taking, and that cubed root, you can take the cube root of any number. Now, if it was, for example, if the power was, let's just say, 5 halves, then I would have some issues, because that's the square root, and you cannot have negative numbers underneath a square root. You can't, at least in the real number system. And that's when you graph. You graph using the real number system. So just be aware of that you want to make sure when you're looking at the domain, if you have rational exponents, that the denominator of your rational exponent, if it's even, then you're going to have a restricted domain due to the fact that this argument, or this radicand, if you want to call it that, must be non-negative. Anyhow, in our case, that radicand can be anything we want. And so therefore the domain is all real numbers. And I'll just go ahead and write that over here. The domain is what we call the R double bar. There you go, R with a double bar. All right, graduating through our mathematics, we found the intercepts, we found the domain. Now, according to our list, we'll go on to the vertical asymptotes, if there are any, and then the horizontal asymptotes. These steps right here are what I think are the pre-calculus steps. So vertical asymptotes and horizontal asymptotes. However, I call them the pre-calculus steps, but they actually involve a little bit of calculus because you're using limits. But let's go ahead and go back and see what I mean by that. Of the two, the vertical asymptote is easiest to work with because you are really looking at the domain of your function. If you have a domain restriction, you might have a vertical asymptote. But if you don't have a domain restriction, you don't have a domain or a vertical asymptote. So I can easily say the vertical asymptote just does not exist. So I'm writing in DNE, not because that's common notation in mathematics, although DNE is common notation in mathematics, especially in calculus. But when you say vertical asymptotes and you don't have any, usually you just say none. However, in an online homework system, you would probably put DNE, and I know a lot of people use online homework systems. All right, so because we have no domain issues, there's no vertical asymptotes. But now we have to move on to the horizontal asymptotes. Now, just to remind you, to find a horizontal asymptote, you would let x go to positive and negative infinity. And if you allow x to go to positive or negative infinity here, I'm just going to do this like this, positive or negative infinity of our function. So of that negative, I'll factor out the -6 because that doesn't actually matter. X minus 2 to the 2/3. If this becomes a finite number, then we have a horizontal asymptote. Remember, horizontal asymptotes are considered end behavior of a function. So if I were to draw out a function and the function looked like this, so over time it's wiggling and wiggling and getting closer to the x-axis, then I would say as x goes to infinity, our horizontal asymptote is y equals 0 because that's the x-axis. But in this case, as x goes to infinity or negative infinity, this is not finite. And because it's not finite, we do not have a horizontal asymptote. You can see that if x goes to positive infinity, you have infinity minus 2, cube root, and square. That's infinity. And then times a -6, it's a negative infinity. I'm not really worried about that. You could, by the way, get the view of the end behavior here. Even though you don't have a horizontal asymptote, you could say, well, as x goes to positive, actually, or negative infinity, this is going to go to negative infinity. The reason why both cases go to negative infinity is if you allow x to go positive infinity, minus 2 is still positive infinity. Square it it's positive infinity, multiply it by -6, it's now negative infinity. If you were to plug in or allow x to approach a negative infinity, well, lose 2 more, it's still negative infinity. Eventually, you're going to square that negative infinity, which gives you a positive infinity, times a -6 out front, which gives you that negative infinity again. So in both cases, I know as x goes to plus or minus infinity, so as I look to the edges of my graph, I know my function is diving down to negative infinity. And that's a good piece of information to know. Even though in this step we're asking what is or are the horizontal asymptotes, the reality is that it also is very helpful, even if you don't have a horizontal asymptote, to decide what the end behavior is. And in this case, it's negative infinite in both directions. So that's a good thing to do. For those who are already a little bit beyond this and have dealt with oblique asymptotes, you would at this step probably look for oblique asymptotes, but we don't do that right now, not yet. All right, so now that we've gone through our elementary algebra, intermediate algebra, and then pre-calculus mixed with a little bit of calculus, we will now step into our actual calculus, like our derivative stuff. So I'm going to go ahead and on the left-hand side here, take my first derivative, so f prime of x, and that is going to give me a negative, 12 thirds, but obviously 12 thirds is -4. So that'll be that -4x minus 2, and then to the -1/3, and then the derivative of the interior of that function would just be 1. And so that's our first derivative. Now remember what you need to do here. You need to find the critical numbers of our function f. The critical numbers occur when the derivative is 0 and when the derivative does not exist. Notice our domain is all real numbers, and yet the derivative actually doesn't exist at 2 because this is technically -4 over the cubed root of x minus 2. You have to watch out for that. So f prime does not exist at x equals 2. Also, f prime is equal to 0 when that derivative right there is equal to 0. But the reality is that a fraction only becomes 0 when its numerator is 0, and that numerator will never be 0. So we only have, punchline here, we only have one critical number. It occurs at x equals 2. Now, I've been kind of stating that as you go through these problems, you should keep things clean and really kind of organize your work. What I'm going to do here is I'm just going to showcase kind of what I would do as an intermediate step as I'm moving through. I would go ahead and put an open circle, and in this case I put red, but open circle just means to me that that's where the derivative doesn't exist, and I'll put the number 2 there, and this is our first derivative. Now, that 2, again, is a critical number. The derivative might change signs on either side of that. So let's go ahead and take a look at the derivative, this guy right here, and plug in values that are greater than and then less than 2. If you plug in a value into this derivative that's greater than 2, you'll have -4 over a positive number, and that is going to be a negative derivative. So our derivative will be negative over there, which means that our function will be decreasing. Now, if you plugged in a number less than 2, and a nice number to plug in that's less than 2 is 0. So if you plug in like 0 to our derivative, you would get -4 over a negative number, which would be positive. So therefore, we have a positive derivative prior to 2, and that means our function is increasing on that interval. So far, we've done pretty good. Note that because our function was continuous, right? Our original function, its domain is all real numbers. There's no vertical asymptotes or anything like that, no jump discontinuities. It's a continuous function. Then our derivative switched signs at x equals 2, it went from an increasing to it has our function going from an increasing to a decreasing function. That means that at x equals 2, at that critical number, we have a local max. Because again, your function went from increasing to decreasing. Notice how I drew that, by the way. I didn't do increasing to decreasing. I did it as a function whose derivative doesn't actually exist at 2, because that's likely what we're dealing with, a derivative like that. All right, so let's go ahead and do one last derivative here before we start graphing. So the final derivative is based off of this first derivative, and that final derivative is going to be f double prime of x is equal to a positive 4/3 times x minus 2 to the negative 4/3 power. Well, that's kind of nice, I guess. And again, we have an issue at x equals 2 because of the division by the cubed root of x minus 2. So, but otherwise, there's no way for this double derivative to become 0. So the critical number of the first derivative will again occur at 2. Now, if you just heard me and said, wait a second, I thought we're working with the second derivative, I will repeat what I said in the last video. The critical numbers of our original function, f, the critical numbers occur when its derivative is 0 or does not exist. So when f prime is 0 or does not exist. Those are the critical numbers of f. Now, the critical numbers of f prime occur when its derivative is 0 or does not exist. That means when the second derivative is 0 or does not exist. So we're looking for the critical numbers of f prime, and we find out those occur at 2. And again, the second derivative doesn't actually exist at 2. All right, that's perfectly fine. But our function is continuous. That's what's important. Okay, so let's go ahead and figure out here the signs of our double derivative. When x is positive or negative, this one, it kind of helps to write this in the form of 4/3 times the 4th power of the cubed root of x minus 2. The reason why it's nice to write it that way is because the 4th power of anything is positive. And so you can see that fraction's always going to be positive. And so our function f will always be concave up. And we have all of the information that we need, except we should probably, I guess we have all the information. I was going to say we probably should write down our critical numbers here as points in this list. But the interesting thing here is the only x values that are critical numbers are 2, and those are already in that list. So it doesn't look like we have a lot to go on, but honestly, when you're graphing using calculus, all of this gives you a very crisp, clean graph. Now, as I did in the last lecture video, I'm going to go ahead and draw out along the top of the page here, both my number lines for f prime and f double prime. And looking at my table that doesn't have a lot of information on it, right? Looking at my table, I know that the x values that I'm really going to want to plot there occur at 2 and at 0. And the y values I'm going to want to plot are going to be at 0 and negative 9.5, roughly. So I'll scale this so that actually I'll keep 0 in the center. And so therefore I'll put 2 a little bit off to the right. Note, both with f prime and f double prime, 2 is not going to exist for either of them as well. They're going to be critical numbers, but they're neither the derivative nor the double derivative exist at 2. So that's 2 obviously. And then I'll fill in all the other information about the function. The function itself is increasing on the left side interval, so increasing, and then it's decreasing over here. And I think I might have written in the last video with the plus and minus sign, so I'll go ahead and do that. You don't have to, but you could totally do that if you want. So this just implies the function's increasing and the function's decreasing. And then again, looking at the second derivative, we have plus plus. So I'll just write that above here, plus plus. And again, that showcases that it's concave up. And I should also mention, because it goes from, the function went from increasing to decreasing, we have a local max at x equals 2. Again, it went from increasing to decreasing. I'll even mention that here. It's a local max. That's pretty much all I have for this function. So I'll graph in the y-axis down below here. So let me go ahead and get a pen going. There we go. There's a good y-axis and an x-axis. And I'll turn off my ruler. I don't really need it now. And I'll plot the points that are listed in my table, 0, negative 9.5. And so the scale I'm going to choose is just enough so that it has, I'll go by 2s here, negative 2, negative 4, negative 6, negative 8, negative 10. So negative 9.5 is roughly right about there, I'll just say. And I'm not going to label it yet. I want to label it after I know where my graph is going to be. And then I have a point at 2, 0. And I want to line it up with my x values up there. So let's see, 2, 0. There's my other point. Now, we have a function that's increasing. I'll actually start at the y-intercept. It's increasing and concave up until it gets to x equals 2. It's increasing and concave up. We'll have a local max at x equals 2. But let's go ahead and do this. And also, I know that the derivative does not exist at x equals 2. And you'll see that very much is the case, because when I go to the other side of 2, the function immediately is decreasing but still concave up. There's only one way for that to happen. It's decreasing but concave up. Notice that's concave up, it's decreasing. So that's a good little cusp that we have going on there. And it's decreasing, by the way, forever. So it's decreasing, concave up forever. On the other side of the y-axis, don't forget that side, it's going to remain concave up and increasing. So let's see, it's just probably going to look like this. Remember, you're drawing from left to right, so it's increasing from left to right. There we go. So this looks to be the function. That's a pretty robust example, and it really showcases what happens when you have your derivative non-existing. You could have kinks or corners, cusps, whatever you want to call them, these jagged points where the derivative does not exist. Usually the concavity will help you with that. The concavity will show you that something's concave up on one side, concave up on the other side, and so you get this weird kind of point there. It doesn't always occur like that. You could also have a derivative that, or a critical number at 2, where your function went vertical for that moment or something like that. So you have to watch out for that as you do your graphing. But that's it for this example, and we'll do another example in the next video.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way, cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Says, listen close, don't talk too much, that isn't cold. Sure, you may really hurt inside. It doesn't justify you to speak too loud and cry.